Okay. Hello, everyone. My name is Zhang Hengfeng, come from Dalian University. It's my pleasure to introduce the work of adaptive multi-scale segmentation fusion network for real-time semantic segmentation. We simply call it ASFNet. First, we think the current real-time semantic segmentation doesn't make full use of multi-scale contextual information, and it could be waste many detail, slow down the speed of running, so its perform will be not very well when we talk about the real-time network. So we propose the concept of multi-scale segmentation fusion, and we will use it to fuse multi-scale contextual information instead of feature maps as usual. In ASFNet, an adaptive fusion strategy based on the attention mechanism uses segmentation fusion instead of feature fusion to reduce the computational complexity. It is very useful, and we think the proposed method is good news to the real-time network. The overall architecture of this network is shown in the figure 1. The whole network consists of a backbone network, an alignment module for multi-scale segmentation, and a fusion module for adaptive multi-scale fusion. In the network, the outputs of multiple stages of the backbone network are used to calculate the output segmentation maps at different scales, which is done by adding convolutional layers to classify the feature maps. The obtained segmentation maps are feeding to the adaptive multi-scale fusion module after passing through the alignment module to solve the final fused segmentation results and obtain the final segmentation results. Since the semantic information of multiple scales of the backbone network is fused, the final segmentation result can achieve a more refined. In ASFNet, we want a faster inference, and so we redesigned the backbone network based on ResNet, including channel reduction, adjusting the downsampling order, and replacing the downsampling convolution with the dilated convolution. At the same time, we designed the alignment module to resize the segmentation maps of different sizes to the same size for the input of the fusion module. In the aspect of network design, we designed a faster full convolutional ResNet based on ResNet 34 in order to have a faster benchmark. As described before, it is mainly to adjust the downsampling order and the channel scaling. The early downsampling of the network can substantially speed up the network inference. However, the faster speed may cause the worse accuracy, which is not our want. So the number of network channels requires further experiment to determine the compromise between speed and accuracy. In ASFNet, we first verify the effect of the number of channels on the convolutional ResNet, including accuracy and speed, based on the consideration of overall performance. We need the trade-off between accuracy and speed due to we want to design a real-time network. So as you can see, a low number of channels can speed up the network inference, but it also reduces the accuracy rate. A high number of channels enhances the performance of the module, but reduces the computational speed of the module. So for ASFNet, finally, we chose to use a backbone network structure with a channel number of 32. The core of ASFNet is the adaptive multi-score segmentation fusion module, which is inspired by the selection kernel network and uses the selection kernel convolution to fuse the segmentation graphs of multiple stages of the backbone network. Throughout the module, multiple segmentation maps are first aggregated into a fused segmentation map based on an initial fusion of pixel level additions. And then weight information is extracted from the fused map using channel convolution. The extracted weights are used to weight the input segmentation maps, and the final pixel level addition fills the weighted multi-score segmentation information to generate the output segmentation results of the final module. So compared with ASFNet, we have the following difference. First, we're solving different problems compared to ASFNet for fusing the outputs of different convolutional kernels. The ASF module is mainly used for fusing multi-score contexts. Second, segmentation fusion rather than feature fusion. The segmentation results are obtained by outputting the features at different stages of the backbone network, using the segmentation results as input instead of feature map in the fusion module. The last, the alignment module. Due to the different problem solving, the proposed ASF module's inputs are split maps with different resolutions and need to add alignment module to standardize the input dimensions, which are not available in ASFNet. So for the ASF module, we conducted more extensive experiments to verify its effectiveness and refine its design. First, we explored the effect of the number of fusion stages on the network. We can see from table 2 that when the contextual information of different stages of fusion gradually increases, the segmentation results are also more accurate. However, when the number of stages of network fusion exceeds 3, the accuracy rate decreases instead of rising. So we chose to use stage 3 for a better trade-off between accuracy and speed. We then further enhanced the accuracy of the network through a series experiments, which including building the alignment module using a semantic flow-based upsampling method, adding auxiliary losses for training, and sharing the weights of the alignment module using a weight sharing strategy. So the final accuracy on our ASFNet training set can reach 73.26% MLU. The loss function is shown in the screen. In ASFNet, we added auxiliary losses to the training of the network, which were set to enhance the upsampling results of the alignment module on the one hand, and to enhance the adaptive fusion capability of the fusion module on the other hand. So we validate our approach on cityscapes and Cambridge datasets. The cityscapes is an urban segmentation dataset with 19 classes. For fire, we only use 5,000 finely labeled images to train our network. And the Cambridge is another straight scene dataset, which images are annotated into 11 classes. The virtualization results on the cityscapes validation set demonstrated the performance of the proposed method. As you can see, the segmentation results are more refined compared to the benchmark network FCN-RES 34. Compared with other real-time semantic segmentation methods, our ASFNet achieves notable results on the cityscapes dataset. It works at over 16 FPS on input images with 1024 times 2048 resolution and achieves an accuracy rate of 70.9% MU. In particular, when the input image size is 512 times 1024, the ASFNet can achieve the forward inference speed at 185 FPS. We also evaluate our network on the Cambridge dataset. The results are shown in the table. As you can see, our approach can achieve 212 FPS in Cambridge test dataset and also achieve 68% MLU. Our ASFNet achieves outstanding performance in efficiency and accuracy again. So in the end, let's take a short summary. In this paper, we propose a multi-skull segmentation fusion module based on the attention mechanism to introduce multi-skull context for real-time semantic segmentation and achieve an effect and accurate real-time segmentation, a semantic segmentation network by fusing the output segmentation maps of multiple stages of the backbone network instead of feature fusion. In the future, we will focus on the application of attention mechanisms to real-time semantic segmentation, including the use of more accurate and efficient backbone network or more faster attention modules. Okay, thanks for your listening. that's all my presentation. If you want more detailed descriptions about this paper, please feel free to contact us. Our email address is on the screen. Thank you.
Okay, thank you, Hengfeng. Yeah. I will ask one question before the audience, maybe they are preparing questions. So I think the main difference between your work and the previous presentation from Professor Lee is that you fuse your in multi-scale information from the segmentation map instead of the feature level, right?
Yes.
How do you think about these two approaches, and why you choose the the fusion on the segmentation map? Did you try the fusion on the feature level?
Okay. First, we want to make a real-time network, so the speed is very important. And we found the most method is use feature maps to fuse. And the result is not very well. So we think the segmentation imagine maybe have a better effect. And
Okay.
when we try it, I find it has lost the computational cost.
Okay, so segmentation fusion will be faster than the feature fusion.
Oh yes.
Okay. Yeah. If there is no more questions from the audience or also the panelists, then thank you for your presentation. We will move on to our next speaker.